Okay, I started the recording. Yeah, go ahead.
Awesome. So yeah, I wanted to briefly maybe bring you up to speed on everything that's been going on in differentiation interface. There's been a lot of activity recently with the goal of making it more suitable to basically all of the SciML and machine learning ecosystem. So the biggest thing that happened is this breaking zero point 0.6 release. And so we also revamped the docs a little bit, maybe just to recap what differentiation interface is. It's a list of differentiation operators. So these are the operators we implement: derivative, gradient, Jacobian, Hessian, vector, Jacobian products, and vice versa. So there are 8 operators in total, and we implement most of these operators for each of these backends. So it goes from Enzyme to forward diff, finite differences, reverse diff, tracker, zygote, and even the brand new mooncake, which used to be called Tapir, which is developed by Will Tibbott. And yeah, so essentially it's a big bunch of extensions, as well as some core machinery, because not every backend implements every operator. And we try to do that by leveraging the specific features of each backend. So what you see if you go to the basic tutorial is that you have a very simple syntax for calling uh, these operators. Maybe I can show you live. So here is my REPL. So I'm importing a few packages. Let's not care about what's going on above for now. You choose a backend. So this can be, in our case, forward diff. And then you define a few functions. F1 is a summing, so it has a scalar output. F2 is a vector output, so if it's for Jacobians, I define the input. And then you can apply the operators that you want. So for F1, which has a scalar output, you can just do gradients, and you get the gradient that you expect. For F2, which has a vector output, you can either call it like that, just Jacobian of the function on X, if you have a non-mutating version, or if you have a mutating version, you just pass the input Y, and it works. So what's interesting about differentiation interface is this notion of preparation. Each backend has some specific behavior on how to speed up repeated evaluations of an operator. For instance, I can do here prep equals prepare gradient of F1 on my backend and my input. And that generates an object which is not very, like, it's not very important what's inside it. What's important to know is that you can reuse it to speed up every gradient evaluation from now on, as long as the input is more or less the same as the one you prepared with. So now I can do gradient of F1 and I pass the preparation object. And of course I get the same results, but as we can see, it's much faster. So if I do this, and if I benchmark it against the version that uses the preparation, we see a significant difference. In the case of forward diff, what this preparation does is allocate some caches. In the case of reverse diff, it allocates a tape, etc., etc. So here we gained like about a third of the runtime, and we could gain even more by using the gradient in place. The other big thing that you can do with differentiation interface is sparsity. It's not necessarily really important for machine learning, except if you want to do second order optimization, because in those cases, you're going to end up with Hessian matrices, which oftentimes are very large because it's n times n. And if you use a sparse backend from differentiation interface, then you automatically generate sparse Hessian matrices, which are, that means you don't need to compute every column with a Hessian vector product. You compute just as many Hessian vector products as needed. And this all relies on an ecosystem that we developed with Adrian of sparsity detection and sparsity coloring, which means that it's finally feasible to do large sparse Hessians in Julia. it used to be that sparse tools had some functionalities to do that, but Hessians were never really greatly supported, and especially the colorings were really bad. So now we have basically as good as it gets in terms of colorings and sparsity detection. So these are the features that have been there for a while. And the last one I want to mention is this notion of passing several arguments, because that was a request from many users, and that's what we brought in 0.6. So imagine you have a function that's not just a function of x, but a function of x and some constants, for instance. So here you see my multi-argument function takes a function of x and then multiplies it by a constant. I can now, with differentiation interface, take the gradient of this function with respect to the first argument without building a closure. What you would have done before is build this closure and then use the function which takes a single argument. And while that's necessary for most backends, because most backends only take a single argument, there are some backends that can accept multiple arguments. And for those, we leverage this opportunity to have some optimizations, the typical case being Enzyme. So that's the big thing that we brought in the latest version. And now we think it's advanced enough that people can really start using it in performance sensitive contexts. Of course, as soon as I start suggesting that, people just rain down on me like the Holy Ghost, saying this is slow and that is slow. And if we hard code everything, then everything is faster. To which I answer yes, but then you lose the benefits of an interface. So right now, if you take a look at Julia Hub to see where we're at in terms of adoption, you see that we're starting to get some pretty serious download numbers, 14,000 monthly downloads. The main reason it's that it's being used by nonlinear solve and optimization. So SciML people have started using this package for their Jacobian gradient Hessian needs. And this means that indirectly we're actually used in a lot of the scientific machine learning ecosystem. And what I hope we might be able to discuss together is, does it make sense yet to discuss about, let's say, Turing integration or integration with other machine learning projects that I may not be aware of? Where do you think it might make sense to try to push this interface? And where do you think it would definitely not be helpful or appropriate? Yeah, so that's about it for me. Last thing is, if we want to talk about deep learning, the guarantee has not changed in the sense that arrays are tested. So the active input must be a number or an array, and the same for the output. However, if you pass something more generic, and if the backend tolerates it, then differentiation interface will just forward it over to the backend. So let's say you pass I don't know, a flux neural network. If you try to give it to forward diff, it will complain. But if you try to give it with autozygote, it will just do what it's told. So I can't guarantee perfect behavior on every possible type of non-array inputs, because that's impossible. I have tests in place for flux and lux support. They're still very basic. They only use zygote. But yeah, so the idea is that for non-arrays, if the backend supports it, I'm doing my best to support it as well. But it's a bit harder to test, of course. So that's something we need to discuss if people want to adopt this more widely. And that's it for me.
All right, cool. Yeah, I mean, I think as far as ML deep learning goes, the multiple args issue, and then at least just forwarding complex data structures to the back end, and not having a hard rule were probably the biggest hurdles to any kind of adoption. Now that those are solved, um,
A thing that's a bit
yeah.
difficult is testing, because what's something that's cool about differentiation interface is it comes with this testing package, um, which looks as follows. You can define a set of backends, and then you can define a scenario where you specify the type of operators you want to test, whether it's in place or out of place, your function, your input, and the result that you expect. Here it's the result of order 1 because you're testing a gradient. And then you have this function test differentiation, which does a lot of things like testing correctness. It can test type stability. It can run benchmarks, etc., etc. But the problem is, for arrays, this is more or less fine, but it gets tricky because when you want to test this on non-arrays, like, I don't know, flux neural networks, the expected result here that you have to provide to the scenario, presumably you're going to get it from one of the backends. Like, you're going to say, okay, I'm going to give the zygote gradient as my reference, and then I'm going to test tracker against it. I'm going to test enzyme against it. And if you do that, well, maybe the backends have slightly different conventions on how the gradient is represented. Maybe it's exactly the same structure, but some fields have been set to nothing. Maybe the integers have been ignored. Maybe they haven't. And so it makes testing a little more difficult because once you have a reference result, you need to define a way to compare to it. It's possible, of course, you can pass a custom comparison function, but that's just a caveat. And that's why at the moment testing on neural networks is a bit difficult, is because every backend has a different notion of what the gradient of a flux chain should be, essentially. Stop me if I'm wrong, but that's what I
Mhm.
gather from this.
Yeah, that's right. I guess the last time we talked, it seemed like if you couldn't provide the testing guarantee, then you didn't want to allow it. But I think what's changed is it seems like you'll allow it, but the we won't necessarily have the testing guarantee yet. Or maybe never. I guess
Well,
you're
at
not
the
necessarily
moment,
promising
there are
that.
some tests. Like, if you look at the tests I run every time, there are tests for integration on Lux and Flux here. Um, so at the moment, what do these look like? Let's see in differentiation interface test, the extension for Flux. So the reference here is the gradient with finite differences. I copy pasted this code from some code in Flux that I think one of you pointed me towards.
Okay.
Uh, and what's interesting is that you can define your own notion of, is my result object equal to the reference object? So in testing, you can pass a custom isApprox replacement that, let's say, will ignore integer fields or will ignore nothing fields, etc., etc. So I just borrowed this again from Flux, but I think that's what was missing for really proper testing with deep learning is, okay, you have two backends. These two backends will have different ideas of what the gradient of a flux chain should be. What matters to me is, can you sort of formalize what it means for these two different objects to still be equal in some sense? And that's what I mean by passing a custom isApprox function, so that during testing, I can call isApprox between the gradient that we compute and the reference gradient in the test scenario. And you can, inside of this function, you can ignore anything you don't want. Here, for instance, you see that it ignores some recurrent network states, for instance, things like that. And then the scenarios, you can just define again a gradient, a loss. The argument is the model, and then the constant arguments that are passed are just the input to the model, because you differentiate with respect to the model itself. So this
Hmm.
is the kind of test suite that I had for Flux at the moment. It only runs for Zygote, and it still has some issues. But if you're interested in trying to integrate this in some documentation, maybe at first, or some test suites, we can definitely add more backends or more scenarios.
Yeah, this is already, I think, um, a lot better than what I had expected from, I guess, the last time we had talked about this. Um, I think the only other thing we discussed that is maybe not here is, and this is a pretty hard problem, um, is like forward diff itself doesn't directly support a complex data structure like Flux,
Yeah.
but there, for people working with Flux models, there is a way to use functors and um, replace all the parameters inside the Flux model with the appropriate duals so that you can actually run forward diff correctly. I mean, it may not work for every single model, but at least it'll work for a simple model like an MLP.
And I guess the issue is to, it's not really to replace with joules, it's to iterate over sort of every differentiable number inside the input, right? Because
Right,
you
right,
can't just call forward diff.gradient. You have to recreate one push forward per input dimension, sort of.
right, right. Yeah.
And yeah, so if we're talking about that, that's something that differentiation interface cannot do and probably will not do, because I've been fighting tooth and nail to remain as unopinionated as possible. And that means that
Hmm.
different backends may return different results if they have different interpretations of a derivative. For instance, we've had recently a discussion on integers. Some backends will ignore integers, others will try to differentiate them. And or another issue is derivatives on a manifold. What happens to a symmetric matrix, to a diagonal matrix? If I
Hmm.
start taking sides on all of these for all combinations of 12 different backends, I can't do anything. So the idea is essentially you can think of differentiation interface as passing arguments in an with at least with the least amount of additional opinions as possible. And indeed, that means forward diff will not support flux models. However, you could define, I guess, if you know how to manipulate functors, you could probably define a function that takes an array, restructures it into a flux model, and then computes the loss. And that function you could in turn pass to forward diff.
Right. Yeah. Well, I guess my question is more like in the same way that you added this custom is a prox function, right?
Yeah,
To be able, like I as a user, if I wanted to use the testing on some complex data structure with a reference backend that isn't really necessarily tested in differentiation interface directly, I could define my own notion of is a prox that's appropriate to me
exactly.
and still use kind of the testing harness. Um,
Yeah.
so will there ever be, and the answer could be no, but will there ever be a plan to add something similar to the preparation, but instead of um, preparing like caches, it's more like, do you get kind of what I'm saying? Like instead of directly calling for diff.gradient, it's possible to do a bunch of push forwards with a flux model. Someone would have to define the function to do that. But is there somewhere in the interface that that person could then hook into to say, this is how you um, appropriately call the lower level functions from this backend to do differentiation with this type of argument?
I I'm struggling to see how this is different from restructuring or destructuring into a vector. Like if the user says, okay, my model can be represented by a vector as follows, here's the list of active parameters, then you can use forward diff by passing the vector and then rebuilding the flux model.
Um, well, I guess one of the things we've struggled with is when you do the rebuild step, getting the types right, and then also that restep being costly in terms of recreating all the structs. And so what you could do instead is replace the appropriate differentiable array um, one at a time in the object itself, and then call your push forward over and over again.
Let's see. So at the moment, this is a part of the code that's not really optimized because so differentiation interface, it has a shitload of extensions, one for every backend plus a few. And it has a core structure for so that you can essentially have every operator if you define just a push forward or a pullback. If you define one of those, everything else comes together. But so there are some parts that are not very well optimized. For instance, this here is the part that computes a pullback from a push forward. So this is essentially what we're talking about here. It's fundamentally what forward diff does to get a gradient. And at the moment, what I do is I map over the Cartesian indices of X and I compute a push forward. So I guess it wouldn't be really difficult to switch this out for some form of enumerate numbers inside flux model. Is that what you're talking about?
Yeah. Yeah.
So that would be one thing we have to switch out. The other thing we have to switch out is this notion of basis vector, because we have to push forward every time an equivalent object with just one coordinate equals to one and all the other
Right.
coordinates equal to zero.
Yeah.
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 And so that's another thing that we would have to sort of overload. But in principle, it's not that big a deal. It's a part of the code that I haven't optimized much because it's mostly for correctness purposes. But if you want to, like, for diff.gradient doesn't call this, for diff.gradient calls its own stuff. But
Right.
if this were somehow performance critical, although I struggle to see the appeal for neural networks as soon as you have beyond like 100 parameters,
Yeah.
we
I mean, it would be like some kind of there isn't an advantage for like standard machine learning stuff, but it would be, I guess I had a particular research project where I didn't end up using Julia because it ended up being annoying to do this uh, map plus basis part that you have here, like automating that for arbitrary models. And so in the end, I just never ended up using Julia. But
I
you
mean,
know,
what could be really easy to do is just here, I switch out this Cartesian indices for uh, differentiation interface Cartesian indices or any function that I actually own, because I own
right,
basis. And then I say,
right,
okay, if you have an input for which you control the type, like the type is yours, let's say flux.chain, then you can overload basis and indices, and this should in essence work, right? I don't
right.
I don't see any other big caveat. So that's actually not a bad idea. At the moment, basis is more or less an internal, but it's definitely doable. Make it possible
Okay.
to overload basis. Because yeah, this is always a problem in forward mode. In reverse mode, essentially you get back something that is a copy of your input. It has the same structure by default.
Right.
In forward mode, it's a bit more tricky. But okay, it doesn't seem out of reach. Any other questions, feedbacks, complaints? I've got lots of complaints, so I'm very used to them. I handle them with grace and dignity.
Yeah, I have a question towards Kyle actually. Um, has Zygote considered doing a similar approach to JAX, where you basically have struct flattening and unflattening functions, and to sort of expect users to define these functions if they want to use custom structs in Flux? Or is that the approach that Lux takes?
Um, what you're talking about, like the notion of like walking a pie tree and things like that?
Right. So, I mean, I might be mistaken, but the way I understand JAX works is that it can take these nested structs and then just turn them into a flat array, flat vector, basically. And it does this with this sort of restructuring mechanism that you mentioned has been an issue in Zygote in the past. Um, so I was wondering whether there's any approach where you just expect users to define this flattening and unflattening operation, because I think that's also what JAX expects its users to do manually.
I can answer that. So I believe JAX will decompose nested structures into an array or a list of arrays rather than a contiguous array because it supports non-homogeneous element types. And that's essentially, I think, what the original intent was behind functors is that you take your custom layer type for your nested model and then you get out essentially at the end a flattened representation of all the parameter arrays within it. And then at some point you can repack it back up into your model struct. Zygo doesn't use functors. I don't really know the history behind that. I think people didn't really want to use functors unless they were using Flux too. That might be part of it. And there are also some competing ideas of what such a package should look like. So the long story short is that Zygo doesn't expect this. I don't know if that answers your question, Adrian.
So doesn't Flux require marking sort of custom layers as functors?
Yes,
Flux, but not Zygote.
but not Zygo.
Ah, okay, I see. Yeah, sure. Okay, yeah.
Yeah, Jax goes a bit further in that functors and Flux only does the basic pi tree where you take like one pi tree node and you unpack it one level and then you repack it back at that level. The Jax pi tree functions will traverse the entire tree and then collect all the parameter arrays. One difficulty there is that parameter sharing, they had no story for parameter sharing until I think maybe like a month ago. And I think it's still experimental now. I don't know what they do for that. So that was one thing that functors had to figure out is how to share like how to tie or share parameters across the structure. That's part of why also but I think that's separate because differentiation interface is not like needs to deal with a lot of these backends can't even deal with a tuple of arrays. They just need to deal with a flat array, right? So I don't know if that would solve the fundamental issue here anyways.
But essentially, as soon as we're talking deep learning, we're essentially interested in 3 backends, right? There's going to be Enzyme, there's going to be Zygote, Tracker, and maybe Mooncake. But that's it, because we're only interested in reverse mode or reverse mode backends, and reverse diff only supports arrays. So,
well, I would say that if you look at what people are doing with Jax, there are a lot of people doing hash and vector products with I don't know, remember, I think it's forward or reverse.
yes.
And that's super easy with Jax because despite it being deep learning stuff, the problem we've had in Julia is that there is no forward mode backend that really besides Enzyme, and like Enzyme is the only backend at this point that does forward mode and can do anything that's not just an array.
Yeah. Oh, so your goal would be HVP of a general struct, basically.
I mean, if we're talking Jax parity, then yeah, because you can do that in Jax, right?
Yeah.
Like you have optimized, quote unquote, second order optimizers that basically take a bunch of HVPs and do some post processing on them to gather statistics for the optimization. But it's just been a dead end for Julia right now because I guess maybe you could do it with Flux if you use a component array. I don't know if it works.
Yeah,
right
you
now,
can definitely do it. What you can do in differentiation interface, which is actually really nice, is you can specify a backend that's a second order backend. So you can say, okay, you want to do HVPs that are forward diff over Zygote. You can do it like that. And then you can say, okay, give me the HVP of the sum or my function f1 because sum is trivial. And then I don't know, 2x. And if you do that, it will fail, of course. What did I do wrong? F1 backend x. Oh, I need to specify tangents in a tuple because there can be more than one. But there, it should work. So you have this mechanism for combining backends, but I agree that at the moment, Enzyme is essentially the only one that can do sort of forward mode on anything. But actually, HVP of something is easier than gradient. Why? Because HVP in forward over reverse, it's just one call to push forward, and the tangent, the seed, is already determined. So we don't need to overload basis. We just need to allow forward diff to propagate duals on more general structures. So if you really want HVPs with forward diff over Zygote, zygote because I don't know, you want an alternative to Enzyme. It's a one-line change, and it happens exactly here. In this forward diff extension, I have functions for making duals from numbers and their tangents. So if I have a number and its tangent, I just go dual. And if I have something else, by default, I assume that it's going to be an array and I broadcast. Right? But this could just be functors.fmap. So essentially, if you wanted to do HVPs with forward diff over zygote, it's a one-line change here to replace this with functors.fmap. And there you get it for free. I just haven't done it yet because I didn't think there was an interest, but you can already do it with Enzyme, that, however.
Yeah, and I don't know if necessarily you want functors as a dependency in diff
No,
interface.
not
That's
necessarily,
a
but
whole, that's
it
its own
could
whole
be,
can of worms.
it could
But it
be a
doesn't need to
kind
be
of
done. It can be done in user code. I
yes,
would assume. Yeah.
or it could be done in an extension that is for diff and functors. If it's really useful. I don't know if many people are going to want this, but you're right that if you want to compute HVPs of general stuff, then at the moment Enzyme is the way to go. But for diff can do it, because while the high level utilities like Jacobian and Hessian are specialized on arrays, the low level machinery is just dual numbers. And as soon as we can put dual numbers into anything, then we can compute these Hessian vector products.
Yeah.
Okay.
Yeah, sorry.
Cool.
I think I went on a bit of a tangent there. Did I address what you were asking about there, Adrian?
Yeah, I think so. Yeah.
Okay.
Yeah, I also have to run. So yeah, sorry, and see you at the next meeting.
See you around.
All right. Thanks for joining.
All right, thank you.
Okay. Well, I guess if there's no more questions
Yeah, let's
or
leave the floor to
commentary.
Julian.
I've actually got two questions, and I don't. I also will say I didn't prepare anything for today.
Me neither, as you can see.
Well, I have even less prepared, and I don't have any time. I'm going to be flying out today, so I'm kind of rushing to get packed because I'm bad at preparing for things. So I'm not going to attempt to show anything today. Maybe just some discussion about related stuff, but no screen sharing. But anyway, so I have two questions. One, I think I probably know the answer to this, but is there testing within differentiation interface for like the major GPU backends? Like what's the GPU testing situation right now?
So at the moment, so this is the equivalent of a startup starting in a garage, right? This we built it from scratch in like 6 months with Adrian, and it is still using free GitHub Actions, which is starting to reach its limits because, as you can see, I need to test every backend for every possible operator on a variety of input scenarios, plus some downstream tests with Lux, Flux, etc. So it's starting to get a bit much for GitHub. And the next step for me is to move differentiation interface to an organization so that I can benefit from the Julia GPU organization build kite. Because that way I can start testing on CUDA GPUs. At the moment, it's only tested on CPU, but, and here's an important but, I have an extension here for JL arrays. I don't know if you're familiar, but JL arrays are basically arrays that work in native Julia, but that throw a tantrum when you try to access indices one by one. So this is a great way to emulate behavior on a GPU. And this has allowed me to sort of GPU proof the entire core of differentiation interface. So I've got this bunch of test scenarios on the GPU. And this has allowed me to certify that anything in the core package differentiation interface itself, so anything you see here, like when the Jacobians call the push forwards, or when the Hessians call the Hessian vector products, etc., all of this doesn't do indexing of individual indices even once. So I don't have proper GPU testing. And of course, most of the backends will actually fail on the GPU. But the core sort of cascade of fallbacks is GPU proofed, which is, I guess, already something.
Great. Okay. Well, when I'll be out this weekend, but next week, I would be happy to help with if I can help with build kite setup.
Oh, that
I've
would be
done it.
lovely because I've never done this. So
Yeah, build kite's pretty straightforward. I think I have admin permissions, and we can take a look at which organizations already have build kite set up that differentiation interface could go to.
I mean, it's
But
probably going to be Julia Diff.
cool. Pretty sure it already is already been added in build kite, so I can just set up your pipeline and we can hook it up for whichever, I mean, just start with doing CPUs for now, and then when you want to do GPUs, it should be reasonably easy to switch over.
Right.
But yeah,
Oh,
I
and
can help
another
out.
thing is that so in differentiation interface test, I have a series of sort of basic scenarios. So these are my default test scenarios, and they could cover all combinations of number to number, number to vector, number to matrix, vector to vector, vector to matrix, etc. And none of them accesses individual indices even once. So all of these scenarios can be straightforwardly ported to GPU, CUDA, whatever arrays. So I really think this is going to be fairly easy to test, provided, of course, that the appropriate backends support GPU execution, which, for instance, is not the case of forward diff.
Yeah, I mean, be prepared for the various non-CUDA GPU packages to blow up in fun ways.
Yay.
AMD GPU, I'm sure, will find a good way to blow up. Metal in One API will be interesting with their various peculiarities. So, but yeah, probably getting CUDA to work should be pretty easy. Obviously, nearly everything is supported there. So, we could take a look at wiring that up and then, get around to doing AMD GPU and the rest afterwards.
Yeah, that sounds like a good start.
And then at some point, I need to, I've been taking a look at what's necessary to get Dagger to support Enzyme specifically,
Yeah.
because Enzyme has a general plan for how to deal with parallelism APIs. So, now seeing these testing facilities that you have, I think my plan would generally be to use that, even if I'm just testing with Enzyme, to start with, to add that to Dagger as a testing utility to help make sure everything works. And there'll be like probably 2 or 3 different ways that I would expect to be able to differentiate through, or ways to call code that uses Dagger that I will want to differentiate through. So
I seem to remember, though, that the main problem will probably be type instability, right? Because Dagger has a lot of dynamic dispatches.
yeah, that will be a complication. But at the same time, so does the task system. There are aspects of it which are type unstable. So should be possible to work around them, and I can always, fiddle around with Dagger to make it work. So
Just a fair warning about this. If you try to use Enzyme through differentiation interface, it won't surprise you to learn that Enzyme is the most complicated backend to support by far. It's not even close. And lots of it is like poorly documented or hard to understand. So I do my best, but every 2 or 3 days I get into a GitHub fight with Billy because he finds some way that differentiation interface calls Enzyme in a suboptimal way. So his message is always, if you want optimal correctness and optimal performance, call Enzyme directly with the lower level functions. Which might be what you need to do to get Dagger to work. I don't know. So definitely do try it with DI, but just remain aware that as far as Enzyme is concerned, I do my best to be generic, but it may come at the cost of sometimes performance and sometimes more problematically type instabilities, which in turn may cause things like seg faults, because Enzyme does not error gracefully.
Yeah, that's okay with me. This adding AD support to Dagger is going to be experimental initially, and I'm prepared for that. I also have familiarity with LLVM, and that has helped me reading through some of Enzyme's codes. So, but yes, I appreciate the warning. And you know, I'm prepared for it to be a pain in the ass, so that's
All
okay.
right.
But yeah, I want to support this. I would love to be able to test that DI works with Dagger and that even just for Enzyme to start with. Probably also forward diff should be easy.
I mean, yeah, I would definitely start with forward diff. Don't start with Enzyme. The easiest one to start with would be actually a finite difference backend.
Well, more from the perspective of using Dagger for deep learning is kind of the direction I'm going.
Right.
Because that's a lot of people's interest and focus, and my own focus is being able to use Dagger for deep learning specifically. Hence why I'm kind of going directly for Enzyme. And I'm also regularly talking with Billy, about the reactant stuff. I mean, we met yesterday anyway, so yeah. Anyway, that's going on. Oh, I had another question about differentiation interface, the testing utilities. I guess the expectation is we can. Okay, no, I don't have another question about it. I'm reasonably happy. Oh, what element types are you testing with? Is it just float 32 and float 64 right now?
At the moment, just float 64.
Okay.
It's just every time I actually have a big problem with compilation time. The tests themselves don't take a lot of time, but compilation takes a lot of time. And one of the reasons for that, I guess, is that in every one of my functions, I need to. You're aware of this rule that Julia does not specialize on function arguments by default. But if I let it happen, that can cause ultimately type instabilities in dynamic dispatch and allocations in scenarios where specializing on the function would lead to no allocation. So I chose the way of slow compilation to guarantee that every time I can, I specialize on the function to guarantee type stability. But that means compilation times are through the roof for testing. And so if I want to test with float 32, I'm gonna sort of just double them, I guess. But I
what
could. It's just
what aspect of specialization is Julia not specializing on? Because to an extent, I would fully expect that as long as the back end is concrete. Well, I mean, you enter with a new if you enter with a new dispatch, type inference is going through and already figuring out all the types of everything as it goes along. So I'm not really sure I understand where the type instability would come from.
it comes from here. This is like the part I hate most about the performance tips. Do you know this section?
Um,
It's because a lot of the functions subtype function, like capital F function, and
Yeah,
then they get
essentially
auto
each
despecialized.
function has its own type. Each function has a singleton type that's type of F. And so for higher level functions that take F and just sort of pass it around, as is often the case in an autodiff framework, and even more so in an autodiff interface, for these higher level functions, Julia cannot afford to specialize by default on every possible argument type. So by
right.
default,
Okay.
specialization is deactivated, but you can trigger it by adding these annotations, which is what I do because at the cost of a lot of compilation, it means that the resulting autodiff calls will be faster. And my assumption in designing DI is that essentially you're going to have one function. Like your neural network is going to be one function. So you compile on this and then it works out because you do hundreds or thousands of gradient calls or millions.
Right. Which, yeah, that makes sense.
It's tough because we don't have incremental compilation, I think is the problem. This is something I mentioned with Zygo, and one thing I wanted to test, but never really had the wherewithal to, because the Zygo test suite is a dumpster fire on a good day, is trying to split out some of the test code into sub packages so that precompiled cache could work, like both locally and on CI. But I don't know. It might be too much effort to do it that way.
But
I
I'm
think,
wondering, Join,
go ahead, sorry.
yeah, what do you expect? Like, I can open an issue about this, but essentially, what do you expect would be different if we test on float 32, at least on GPU?
Oh, is that to me?
Yeah, or to anyone really. Like, what would be the point of testing on float 32 apart from guaranteeing that I don't have a 1.0 somewhere in my code that converts to float 64?
So that actually relates to the GPU point, that if you want to test on Metal or Intel, which I think we should, I think would be good, mostly for the sake of keeping those packages well tested and developed. Those do not support executing basically anything with float 64. And only support float 32 generally, and sometimes like float 16 and other formats. So for one thing, being able to test on those backends at all is going to be required. Required to do it with float 32. The I don't know. I mean, honestly, I just feel like having two element types to test with, and with float 32 and float 64 basically being the most common, I feel like that helps get rid of a good number of bugs that just show up from, silly little things that were, like 1.0s and stuff like that, as
Yeah.
you say. But, I do understand that, from the perspective of compilation time, and not testing an infinite number of things that just takes forever, for now, sticking with float 64 makes sense.
I mean, it could make sense. It's just I might not test it for every backend, because if I test it only for the core code, it's one time, but if I test it for every backend, it's 12 times the time. So
Yeah. What is the sum total of the time required to run tests?
well, let's see.
Like
Last
roughly.
CI run. So it's 1 hour. These tests succeeded in 1 hour in total. No, wait, that's the docs. No, 1 hour ago. Sorry. Actions. I don't know. Last test run. Okay, this one. So DI is the most demanding. Okay, so let's see. It's very diverse. So I parallelize across backends, and I try to group backends that are similar. Another thing that slows down the tests is that in every test file, like I have one test file per backend plus a few more stuff, but in every test file, I do a pkg operation to add the backend. The reason, and of course, it prevents me from doing anything like caching, right? Which presumably would help a lot. But the reason for that is that otherwise, I am absolutely obliged to have an environment where all the backends are present at once, which restricts compatibilities like you've never seen, right? And it didn't even work on 1.6, and even on 1.10, I would have issues. So the trick I found is I parallelize these tests, and for each backend I add it individually, which means it's not part of the test dependencies. So that's one thing that definitely slows stuff down. And if we look at things, okay, it's 5 minutes for chain rules. Some of the largest ones are Enzyme. It's nearly half an hour. Forward diff is 15 minutes. Reverse diff is 10 minutes. This is on 1.10. And some internals are like 10 to 15 minutes. So grand total, ballpark 2 to 3 hours, I would say. It's parallelized, so it finishes in 30 minutes. but the parallelization has limits on a free GitHub account.
I got you. Yeah, and we won't encounter that issue with BuildKite. And so I'm not experienced at all with caching, but I do know that BuildKite has extensive caching support for all different kinds of configurations. So we could talk to Tim Bassard about how we can best cache these so that we can still be able to cache environments without having to add all of the packages within a super,